So far we've talked about two types of bonding, ionic bonding and covalent bonding. All right, there's one third type of bonding that we're going to be learning about in this unit, and that's metallic bonding. All right, and as the name implies, it's the type of bonding that's going to occur in metals. All right, and I want to take a second to differentiate two different types of metal atoms because we've already learned about um, a certain type of metal atom that is involved in a bonding that we've talked about, and that is an ionic bonding. All right, so recall that in ionic bonding, you have to have, excuse me, positively charged atoms and negatively charged atoms, and often those positively charged atoms are metal atoms. So when we talk about metallic bonding, we're literally talking about like the bright, shiny, bendable materials that we commonly think of when we think of metals. All right, even though ionic compounds typically have a positively charged metal cation in them, this is not what we mean by metallic bonding. All right, this is ionic bonding. All right, so for example, when we think of sodium, a lot of times you think of sodium chloride, which is an ionic compound that contains positively charged sodium atoms. But it's also possible to have pure sodium metal. All right, and pure sodium metal is probably something that you haven't ever dealt with before, but it looks like this right here. It's a metal. All right, if it's pure sodium, all right, not sodium ion, but pure sodium, it's a metal. It's shiny when you cut it. And so it's got some interesting properties. First of all, it's so soft that you could actually cut it with a plastic knife. All right, if you've ever, you'd want to wear gloves when you hold it because it reacts pretty easily with water and the moisture in your skin. But if you're wearing gloves and you have a little piece of it, you can actually squeeze it like silly putty. All right, it's very soft. One thing about sodium metal is since it reacts violently with water, if you do throw it into some water, it's going to actually creates a flame. All right, so there's good reasons that we don't see sodium metal a lot in normal everyday things. It does have a lot of use in chemistry applications though. All right, so when we're talking about metallic bonding, we're going to be talking about what holds these sodium atoms together. All right. So as a quick just summing that up, ionic bonding is the type of compound that you have where you have positively charged metal atoms with negatively charged, generally non-metal atoms, but metallic bonding is just pure neutral metal. And we're going to call it neutral for now. And as you'll see, it's not necessarily true to say that these are neutral atoms. So to start with this, we're going to start with the simplest type of metal atom, which is going to be lithium. And what I've drawn here is just two examples, two Bohr diagrams of neutral lithium atoms. All right, and if you take a look at this, all right, this thing right here would be completely neutral, and this thing right here would be completely neutral. This is the way that these atoms really existed, there would really be no reason for these atoms to stick to each other. All right, just two neutral objects next to each other don't create a reason to stick. All right, but we know that metals are solids. All right, and the fact that they're solids means that their atoms want to stick to each other. All right, so why is it that the atoms want to stick for these neutral atoms? All right, so to understand this is to understand that not all the electrons in metal atoms are the same. All right, the valence electrons in metals are mobile. All right, meaning they move around very easily. All right, so to explain this, I'm going to just use this little cartoon drawing. I've got 4 lithium atoms right here, 4 lithium atoms right here, and essentially the theory with metallic bonding is that the inner electrons and core stay with the individual atoms. all right? But the outer electrons, the valence electrons, are free to move back and forth between all these atoms, all right? So if we had these 4 atoms here at one point in time, right, and notice I've represented the valence electrons in different colors and shapes here. At some point later, like even a microsecond later, all right, this valence electron might have jumped to this one. This valence electron might have jumped over here. You can see that the valence electrons move back and forth, all right, but the central core of the metal atoms stays put, all right. So that's the key, one of the keys to metallic bonding, all right. So to understand what makes them stick together, though, we need to go a little bit, dig a little bit deeper. And what we're going to do is a little mental exercise, where what we're going to do is mentally strip away all the valence electrons from the lithium atom, and then think about what would the inner part what would its property be. All right, that inner part would now have more protons than electrons. All right, so using this as a little diagram right here. Remember, if it's lithium, it's got 3 protons in the nucleus, and it's got a total of 3 electrons. All right. So, but what would happen if we took away this outer electron right here? If we took that away, there would be 2 electrons, but 3 protons, meaning that that part of it, that middle part of it, is positively charged. All right. So when we're thinking about these metal atoms, instead of thinking of it like this, think of it more like this. We've got this positively charged inner core, but then we've got this relatively loosely held onto valence electron, all right? And it's very loosely held onto, all right? In fact, they're going to be easily transferred with their neighbors, all right? So this electron, you just can't think of it as belonging to this particular atom. It's being shared constantly back and forth with all of its neighbors. All right. So the central part, the central core, which is all the part of the atom except for the valence layer, is, in one way you can consider it a positively charged inner core, but it's often referred to as a cation. All right, and essentially. That's what cations are. They're positively charged atoms that are made when an outer electron is not there anymore or has lost that outer electron. So that's essentially what that is right there. All right. So in the further explanations, we're going to represent the positively charged inner core just like this, just a circle with a big plus. All right. So think of the atoms. So the theory or the explanation that is very commonly used to describe how metals or what metallic bonding is that a metal is nothing but the positively charged cations of the metals swimming in what's considered a sea of mobile valence electrons. All right. So remember, we described this inner core and this loosely held onto electron right there. Well, what if we had a bunch of these atoms? All right, we would have a bunch of these positively charged inner cores, but in between them we would have all of their valence electrons. All right, so in this drawing right here, it's you don't have that sense of one atom owning its valence electrons. It's more like you have 4 atoms and collectively they're sharing all of these valence electrons. All right, so that's what they mean by this sea of mobile valence electrons. All right, and this explanation of electrons accounts for 2 very common properties of metals. All right, the first is that metals tend to be very good conductors of electricity. All right, and if you think about like what a wire is, a wire is, something that can, allow electricity to flow through it very well. What is needed for a wire to function? Well, you need to be able to essentially pump electrons in to one end and pull electrons out of the other end. All right, that's what electricity is. It's a flow of electrons. All right. Well, if you think about it, that couldn't work if the electrons of this material here weren't allowed to move. All right. If each of these atoms held on to its valence electrons tightly, there would be no way for electrons to travel through this substance. All right. So since metals allow, since these atoms or these electrons are free to move back and forth between these atoms, if you were to do something where you pump electrons in on one end and pull them out on the other, there would be an overall flow of electrons through that material. All right. And this is what happens if you attach it to a battery. All right. A battery is something that does that pumping in and pulling out. All right. Keep in mind, if you don't have a battery attached to this wire and it's just a piece of metal sitting there, these electrons are still moving around. They're just moving around randomly, and there's no overall movement towards the right or to the left. All right. It's only when you apply that voltage source that happens. All right. Another property that this explains is what's considered the malleability, or the ability for metals to bend. All right. So the way this is explained is to think about these valence electrons as essentially providing a lubricant between these cations. So if you apply some pressure, like if you were to hammer on these atoms here, instead of breaking, they can more or less slide past each other, all right, and create same material, just in a different shape.